Good morning. Welcome to our Considerations when Designing Houses of Worship webinar. I'd like to introduce Dale Shirk, Senior Applications Engineer from our Loudspeaker Solutions Group. I'll pass it over to you, Dale.
Thank you. Good morning. My name is Dale Shirk. I'm Senior Applications Engineer. I was with Community coming up on about 4 years. Prior to that, I spent 25 years as an independent contractor on my own business, and several years before that working for other people in the industry. So, designing sound systems for houses of worship, something I've done most of my career. Let's get started. 4 questions we need to answer. Number 1, is it loud enough? Can people hear? Number 2, can everybody hear? Is it loud enough for everybody? Or is there dark corners someplace? Number 3, can everybody understand? And number 4, will it feed back? Question 1, is it loud enough? First, we need to get into some details about how we actually measure sound level. On the left here, we have a waveform of a recording of a sentence of speech. Modern electroacoustics began in 1915. And on the right, we have pink noise, which is what we use to measure loudspeakers. So the loudspeaker measurements are going to be used with pink noise. You can see it's much higher density. Both reach the peaks, speech only in the negative in this case, but there's much more energy in this. The crest factor is what we call the difference between the peak level and the average, not average, actually RMS, but the effective value of the total signal. So pink noise has a 6 dB crest factor, where speech can be 12 to 16 dB crest factor. When we measure this with a sound level meter, we measure speech, we're going to measure much lower than we would measure pink noise. We need to take that into consideration in comparing speaker measurements to actual live speech. So appropriate level for speech, target levels at the seat. It should be 15 dB above the noise level, ideally 25 dB. In a noisy environment, maybe an auction or a game, sports, you may be less than 15 dB, but at that point, noise is starting to cut into your intelligibility. 70 dBA average speech level in a room of quiet, attentive people. If you're a geek like me and take a sound level meter into the living room and you have guests, you will measure the conversation going around the room at 68 to 70 dB. If you've got a noisy crowd, an auction or a game or something like that, your speech levels need to be much higher, 84 dB. You have much more noise to get over. So you add the crest factor to the speech level to get the maximum level, which would be maximum output of the loudspeaker. We use 96 dBA as a target design level for non-professional sports, high school football and so forth. Professional sports can be a little more energy to them. We take that 96 dB, subtract the 12 dB crest factor for speech, and you will measure about 84 if you take your sound level meter into the stance. So that's kind of where we understand the difference between what you'll measure with speech and what you're designing, from a spec sheet. A quiet traditional church can use a lower target level. High energy contemporary worship can be higher, quite a bit higher. Inverse square law for outdoors or indoor direct sound only, which is typically what we consider. You can use inverse square law to calculate from the distance from the seat. Your seat's out here, say you're 16 meters away from the speaker, 24 dB dispersion from the loudspeaker. Because it's spreading out over the distance, you add 24 dB to get back to the loudspeaker's reference distance, and you can know what output you need from the loudspeaker. Or you can just try the loudspeaker in the computer room model, see if it's loud enough. We'll get into that in more detail later. Question 2, can everybody hear? Even coverage is the single most important consideration. It's also the most often overlooked. When the trunk slammers or the people that design something that put a speaker here that looks about right, they're typically going to miss it on the coverage because they're not considering, does it get to the front corner? Is it too loud, right in the middle? So we need to design for even room coverage. It's pretty much job one in system design. Direct sound coverage mapping programs are free. Numerous manufacturers produce their own. We prefer to use Ease Focus 3, let somebody else develop that. We can concentrate on building loudspeakers. None of the programs will tell you where to put the speaker. They only tell you what happens if you put it there. So by quickly answering, well, what if I do this? What if I move it up? What if I move it down? What if I move it front or back? And you can try up various ideas and see what works best. And as you gain experience, you'll go, okay, yeah, I know what I should do with this. It's, you start to understand how sound covers in a room. How good is good enough? How even do we need it to be? For critical active listening, which is what a church would be, I go for plus or minus 2 dB at 4 kilohertz over 95% of the seats. And I try for plus or minus 3 dB over 100% of the seats. There you see the graphics of from Ease Focus showing that. Here's your target level. You've got plus 2, plus 1, you've got 35% of the seats. Only 1% of the seats falls into the minus 3 category. So use this distribution to see if you've met your target. For sports announcement paging, plus or minus 3 dB or even looser may be sufficient. It's not a critical listening where you're trying to communicate a complex and perhaps arbitrary message. Other frequencies, 4 kilohertz must be right. If 4 kilohertz isn't right, you need to go back and make it right. So you design to it. 1 and 2 kilohertz should also be very even. It's pretty easy to get those from 1 kilohertz to 4 kilohertz. Get those right. Higher frequencies are nice. They add sheen, they add presence. Lower frequencies are more difficult, require larger devices to get even coverage. You can't, it's much larger waveform. It's going to take a larger device to direct it the way you need. An old saw from days gone by is go for even coverage to as low a frequency as budget and aesthetics allow. Which speaker to use? Something that's not maybe talked about as much as it should be, but loudspeakers have a preferred tilt angle for which they will cover the largest audience area evenly. Look here on the left, I have it written as a 60-degree speaker. It might be a 50 or 40, I'm not certain. But there's my mouse, here we go. This line along the bottom represents the seating area. The colors, of course, are the levels of sound at different distances and angles and so forth. And everything within the plus and minus 2 dB range is masked off. So it's all green. It's not shown where it falls in that, but that window falls within the window of acceptable level. So here we've got the entire audience area within this acceptable level. And you could draw this line through a different direction if you were doing a different angle on the speaker, but it wouldn't. This direction is where it gets the longest line. In other words, the most area covered evenly with that speaker. Down here, we've got a narrow speaker. This is going to be an antithesis of some flavor. and you see a much shallower angle. We can get a very long angle through here. If we were to tilt this speaker down steep and the audience plane goes through this direction, it's a very short audio. It's not covering very much area. So when you're looking at a new speaker for the first time, take a look at where it covers. Try to determine what it prefers as far as a tilt angle. Speakers with a larger vertical angle prefer a steeper tilt. Narrow vertical angle, like an antithesis or a line array, wants to be at a very shallow angle, and obviously a lower mounting position then as well. Which speaker to use in the horizontal? Wider horizontal patterns generally cover more area, more floor area than narrow angles. Here we see on the right a 60-degree angle, and this isn't, I mean, it's got a huge hot spot in the middle, so we're already beyond that. I mean, it's not really acceptable area. Here, 120 degree, we covered this much. These are the same speaker, just a different horn pattern, same angle, same height, same distances. So a wider horn tends to cover more floor area than the narrow horn. Speakers should also have a suitable range, frequency range, output level, quality for the program material and client's expectations. Where to locate the speaker? Well, obviously in front of the listeners. Locate the speaker such that the sound comes from the same general direction as the acoustic sources that you see on the stage. You don't want to see someone up there talking and hear them from somewhere around behind your head somewhere. So that's sort of basic, but some people forget it. In really small rooms that barely need sound reinforcement at all, sometimes you can violate that and make your speakers seem like just a room reflection. Make sure there are suitable rig points, building attachment provisions. Beware of visual sightline issues, video screens, stained glass. Do not put your big box speaker directly in front of the face of Jesus on a stained glass window, even if that view is only from the balcony. In this case, that speaker actually had to come down. This curved surface in here was causing reflections back down to the microphones. We ended up putting sound columns on the sidewalls. We'll talk a little more about that later as well. Where to locate the speaker? Again, aim the loudspeaker at or near the furthest seats it is intended to cover. This is the same graphic we saw before. And you notice the aim line is at the, if we were to aim it higher, and our audience plane come across here, now we got more sound up on the back wall than we have in the seats. That's not good. If the front is too loud, and again, let's look at this a little more. The loudest point is going to be about a quarter to a third of the way back. And in the front, here we need to look at the front seat versus how far in front of that the speaker is. So in this case, we for some reason had to have the speaker moved further out here, we would be missing some seats and we'd have to maybe add some fill speakers. So that's some things to look at. If the front is too loud, obviously you get a loud spot here. Move the speaker higher and tilt it down a little steeper. Don't move it so high that you run into the roof. Don't forget where the roof is on a 2D model. It's easy to not see that. Or use a smaller vertical angle. Use a little tighter vertical so that you don't get this hot spot here. If the front's too quiet, again, move the speaker down. Use a wider vertical angle. There was something else I was going to point out here that I forgot. And yeah, these will change with frequencies, but we're looking here, I believe 4 kilohertz is what we start with, and then look at the rest. So using fill speakers. First, try a little bit harder to get good coverage from the main speaker. A single source is always best, always sounds the cleanest, always the most intelligible. If you have to use fills, you have to use fills. They're typically needed in the front corners of a rectangular room. Here we have a section of a rectangular room, got a single speaker overhead center, covers most of the rear is easy to cover. That's what I wanted to point out the last slide. The rear is very easy to cover. If it's the front corners where you and the front edge, you know, do we match the front edge, or do we have to fill in? That's where it becomes more difficult. So here on each side, we've got this little yellow triangle, the dark area that we need to fill in. We could fill it from either of these positions, but if we put the speaker here to fill in, now we're going to create problems out here in the center because the sound is going back toward the other one. Sound from the main speakers going this way, keep the sound from the fill going in the same general direction. It's much better to fill from this direction. In a small, and again, in a small room, you can violate this a little bit more. In a larger room, you're going to run into timing issues. Here we've got time so that this speaker so that it works out here. Out here we get a late arrival from it. It's if you keep sound going the same direction, your arrival times tend to work out better. If possible, reduce the throw distance from the fill speaker to the filled area. Allow the fill speaker to run. This allows the fill speaker to run at a lower level and less detrimental effects in the other areas. Only fill the frequencies needed. If you go back here, this speaker, the low frequencies will cover, you know, it's omnidirectional. It'll cover, be as much low frequency in here as there is out in the center. So we don't need to fill the low frequencies. But that little fill speaker only fills mid and high, maybe from 500 hertz up, something like that, depending on the size of your main speaker. If you add additional low frequencies, you just create more problems in other parts of the room. Delay the fill speaker, even if it's right next to the main speaker. This is I could do a whole another webinar on this concept of alignment and misalignment. But basically, you'll want to intentionally misalign by a couple wavelengths so that you don't get the deep comb filter nulls. And that's something we can, if you have questions about that, you can ask me offline. Question 3, can everybody understand? Speech intelligibility is predicted by a speech transmission index, which is a number from 0 to 1. It is calculated from modulation transfer function, which is a much more mathematical thing. Modulation, here's again, it's our speech clip. These are sounds that are turned on and off, and they're different frequencies. For instance, this is modern acoustics. The hiss of the T or the C here, that's a high frequency. So the different frequencies and they're turned on and off at different rates. So that's modulation. Modulation transfer function looks at frequencies from an octave bands from 125 to 8 kilohertz, and it also looks at modulating or turning them on and off at rates from, I think, a quarter or a half a hertz to 8 hertz or so. So how quickly they're turned off can affect it. So if we, and I didn't put the audio clips in these, I guess I could have, maybe I didn't do that. If we look at this word, this is the word modern. So it goes modern. Right here is the D is formed by putting your tongue up on the roof of your mouth and cutting the airflow off. So that's a modulation. So when we add reverberation to it, it fills that gap in. We can't find it. Where this goes modern, This comes out sounding like modern. You lose that. Where are these modulations in here? They're completely buried. Noise would do the same thing. Noise would be a continuous signal, 1 or 2 tenths units here. The same would tend to cover up the low stuff. The high stuff would stick out of it, whereas reverberation is driven by the speech itself. So if it's higher, it fills in from the highest points in the signal on down. But the noise and reverberation fill in those gaps between the speech formants, reducing modulation depth, and therefore reducing intelligibility. Reverberation time alone is not the only metric needed. Room volume comes into play in determining the reverberant level and interference to intelligibility. If you have 2 seconds of reverberation in a boardroom or conference room, that's a terrible room. That's going to be really difficult to work with. 2 seconds of reverberation in an arena, it's wonderful. It's dry. It's great. Intelligibility won't be a problem. So we need to know, we always talk about the time only, but we also need to understand the time must be qualified by how big a room we're talking about as well. So in the following points, I'm talking about a medium-sized house of worship, church from 200 to 500 seats, something in that range. If the RT60 is 1.5 seconds or less, there will not be reverberation-related intelligibility issues. If the RT60 is 1.5 seconds to 2.5 seconds, then you got to be a little more careful. Make sure you cover the audience evenly. Don't spill excess sounds on the walls and the ceiling. For longer RT60, modeling in a 3D program capable of evaluating intelligibility is recommended. Then that's building a full ease model where you can put the surfaces in. You can put a measured reverberation time in with a known volume and generate actual intelligibility predictions from the model. That requires much more time and room information, typically more than we will get involved in our free design services. That's something you should be paying a consultant for if you've got a particularly difficult or questionable room. Longer RT60 rooms may require a line array. We'll typically, if we think it's marginal, we'll go for an antithesis line or an IV6 line system because it'll give us the best intelligibility in a longer room situation. Additional intelligibility issues, echoes. And by that, I differentiate echoes from reverberation. Reverberation is the general sound bouncing around. Echoes are specific, repeats of the sound. Sometimes they arrive in close enough in time to the original that they're difficult to hear as an echo unless you cup your hands around your ears and turn toward the sound of the surface that's reflecting. But the echoes can come from rear walls, from balcony fronts, concave architectural features. These can be difficult to assess off-site. Actually, they can be difficult to assess on-site as well. If you put a loudspeaker on a tripod up on the stage, you might not be energizing the surface that's causing the echo, or you might not be at a place where you can hear that return. It might return up in the air somewhere, not down at the seats. It's much easier to study with a 3D model. Once you have an accurate model, you can put a source and a microphone wherever you want and see where those echoes are going to land. In some cases, you can choose to put a speaker in a place where it won't trigger the echo, or where the echo, the focused sound happens above the audience level. For instance, in the Catholic Church that might have a high dome, if you complete the circle of that dome, the dome is a half sphere. If you complete that sphere, in your imagination, and your loudspeakers or ears or microphones do not fall within that circle, you can probably ignore it. Not always, but most of the time. So that's a good way, does that dome focus sound? Absolutely, but it focuses up there 40 feet in the air where it doesn't matter. It'll disperse again until it travels back down to the floor. So that's what it's easy to study in modeling and difficult to study in person on site. And again, that level of modeling is beyond the scope of services we offer for free. That's things you would hire a consultant for. Almost, if they must be treated, almost always requires acoustic treatment solutions. Like I said, sometimes you can hide it by where you put the speaker, where you aim the speaker, and not trigger the issue. But if you really need to fix it, you need acoustic fixes for acoustic problems. Other issues affecting intelligibility: distortion. If the paper cone is torn and it's buzzing, that's adding new frequencies that weren't in the original signal. Frequency response problems. If the high frequency driver is blown and it's all muffled and muffled sound, you're not going to be able to hear intelligibly. If someone's put a smiley face on the EQ and it's all boom and tiz, that affects intelligibility. Noise. If the air conditioner kicks on, you hear the belt screeching and the air whistling and the motor's rumbling and everything. You might hear it and think, well, okay, I can still hear the person talking, but all of a sudden you have to concentrate much harder to understand what they're saying. So that's why we like to go for quiet low background noise in houses of worship. Question 4, will it feed back? The answer is always the same. Yes, if the gain is turned up high enough, it will always feed back. The real question is, will it meet the customer's expectations regarding gain before feedback? You need to manage the customer's expectations a little bit regarding talker level, reinforcement level, and microphone operating distance. If a person wants to talk quiet with a microphone at arm's length away, they're going to be reinforced at quiet levels. You're not going to be able to get really loud, energize a Trump rally crowd or something like that. You're going to have to either yell loud or talk close to the microphone. If you want to sound like a rock and roller, you got to treat the microphone like a rock and roller does. Designing for good, you can aid the situation in some respects by designing for good gain before feedback. Minimize direct sound fill to the platform and microphone areas, especially at mid-high frequencies. Low frequency spill is kind of unavoidable, but if you need to push the gain, you got a quiet talker or something, the sound operator can always roll off the low frequencies and kind of get around that. Avoid reflecting surfaces right in front of the loudspeakers. Can return energy to the platform. That picture I showed of the loudspeaker in front of the stained glass window, there was a reflecting surface above the speaker that returned energy to the microphones. I had another situation where a loudspeaker was aimed, overhead center at the audience, but right in front of the loudspeaker was a lighting well, and this reflected sound back down into the microphones. I ended up putting sound absorbing material, flame-proof sound absorbing material in the light well, and they got much better gain before feedback because we weren't reflecting the speaker right back to the microphone. What about stereo? You hear a lot of people say, well, you can't do stereo PA, it doesn't work like it does in the living room. Well, maybe yes and no. If you're doing stereo, each channel should cover the entire audience area. Left speaker has to cover the whole audience, right speaker has to cover the whole audience. That can be a little difficult. Excuse me. You must maintain no more than 20 milliseconds, or worst case, maybe for a few seats, 25, arrival time difference between adjacent channels for any audience seat. This limits the width. Can't have this, speakers 70 feet apart. It also favors high loudspeaker trim heights. If the speakers are higher, the arrival time difference between them is not as great as if they're down at low levels. Two-channel stereo, which is what people think of when they think of stereo, will not produce a phantom center channel image, except in the center aisle, which no one's sitting at. However, it can still be useful adding spaciousness and can be relatively inexpensive in a narrow room. If you use stereo, you can sometimes use that instead of fill speakers over center speaker, instead of having to fill the front corners from a center speaker. And it can surprisingly be sometimes as little as 10 or 15% more than a mono system. So certain rooms it can be inexpensive. Three-channel stereo, which is, we may or may not have known that we've been listening to that for decades. It's called Dolby Surround, where the music is in the left and right channels, the dialogue is in the center channel. So it does work quite well. It's been done a long time. The original stereo work done by Bell Labs and so forth in the 30s was three-channel stereo. The two-channel was a cutback on it when you could get a phantom center channel phantom center image if you sat in the center. So yeah, you design the center speaker for a firm image, good clarity, optimized for speech. In the center, spacious, musically optimized left and right. It will be higher cost, especially with the console. In the days of analog, you really had to go to a high-end large format console to get LCR panning. And by that, I mean that you pan from left to center to right. You don't pan from left to right. You never put anything in the left and right the same signal. Lost my train. Today's digital consoles, LCR panning is just a matter of throwing some extra code in, so it's not. There are low-cost LCR consoles now. It can be used in wider rooms without violating the arrival time difference, because we're not concerned with the time difference between left and right, only left to center and center to right. So we can be effective in a larger room. Let's talk a little bit about different types of buildings and how that affects the sound system. And these, you might recognize these graphics from our design guides. Traditional shoebox building, overhead center with fills, just like we were talking about here. That's shown in this little image here. We could also cover this same room in stereo from the left and right corners, either mounted high with point source or low with emphasis, if we can careful of the arrival time differences between left and right there again. Wide fan or diamond shaped room. And here, this is a terminology thing. You will hear this referred to as LCR. It's not LCR. It's a left speaker covering the left audience, center speaker covering the center audience, right speaker covering the right audience. It's called an exploded cluster. Same as a cluster, only they're spread out in space between them. Exploded cluster for a wide fan-shaped room. Stereo would be very difficult. You would have to have a speaker on the right side that covers all the way over to the left, and that becomes difficult to do. With a narrow room, is much easier to do stereo in. Cruciform shaped building. This would be some of your traditional Catholic or Lutheran churches. Again, these are typically high ceiling. They are hard surfaces. They are reverberant. rooms. They're meant for organ and choir music, slow music, majestic music. Getting speech intelligibility can be a little bit difficult. We typically will use emphasis columns to provide intelligibility because of reverberation in the room. Transept shape obviously has seating off to the side, so we need to put an emphasis speaker, separate speakers covering the transepts. Long, narrow, here again, it's not too different than the other church we looked at before. Here again, this can be covered down low with emphasis on the columns. It could be covered overhead center. We could probably cover, put an IV6 array up in here that would cover the seating and maybe the balcony as well, with a larger array if they don't mind the physically, visually larger speaker and need that sort of output. Point sources, because of the length, you may need an additional delays in the back. Here we got emphasis columns from the front, and then a second fill in the back, and also fills for the balcony, over balcony and under balcony in this case. Building types. Some churches like to use spaces that were not originally meant for church. Some younger churches do this. Retail and office space reclamation. The Kmart that was in the hot section of town 30 years ago is now abandoned, and it's for sale cheap. And it's got a big parking lot, so why not make a church out of it? It's good space. It's low cost space, often has limited ceiling height and has posts throughout. So that's something you need to work around. Line arrays are useful. They can cover more distance from a low trim height than a point source. If you use point sources, you may require delayed speakers or delayed rings of speakers if it's a wide fan-shaped room, just because it covers the wide and deep aspect of the room ratios. Conversion of a traditional church for contemporary worship. This is another thing that happens from time to time. The grand edifice in the center of town, the congregation is old and dying off, and a young congregation wants to buy it and use it for contemporary worship. I know of a church in my area that did that and sold the organ and some stained glass windows and paid for the building. Now, they weren't done spending money yet. They had to do some fix up and so forth, but an acoustic space meant for choir and organ is too reverberant for contemporary music, especially low frequencies. We want the thump of the kick drum to hit us in the chest and then go by and not come back again. That requires sound absorption. Line arrays can provide speech intelligibility, but can still have music clarity issues. Again, you have to almost make it sound thin because of the low frequency support that the organ wanted. We don't want that for modern music. Acoustic drums, instrument amps, floor monitors can over-energize a reverberant field, even with the house PA turned off. You play through the house PA, might sound all right, but with all the stage noise, it just turns everything to mush. The solution for that, in-ear monitors, electronic drums, modeled amplifiers, or amplifiers in a back room, mic'd up in a separate space. Keep the stage, reduce stage spill, and improve clarity. Use a quiet stage setup. Acoustic absorption, while expensive, is still the best solution. Concentrate on the stage area and also the rear of the room, particularly if you've got a line array directing sound toward the rear. Make sure when it gets to the back of the church, it stops and doesn't bounce around from there. Worship styles in the sound system. What do we need to consider for different style worship? Traditional liturgical Christian churches, which is the room we were just talking about, the music is organ, piano, it's acoustic. Light instrument reinforcement may be used sometimes through the same sound system, but often through an alternate system, so you don't have to worry about that. Audience is reverently quiet and attentive. If it's speech only, moderate levels are usually sufficient. On the opposite end of the scale, there's contemporary Christian with a full theatrical production. Rock and roll levels up to 110 dB. The vast majority of churches fall somewhere in between in something we call blended. Worship style is much less dependent on denomination than it was 40 years ago. When I got started in this business, you could look at the sign out front of the church and you had a pretty good, you knew what the denomination, what the church affiliation was. You had a pretty good idea what went on inside. Today, that's quite a bit different. You need to find out what the client does, what he needs. There are high energy, contemporary worship in a lot of different denominations that would not have had that years ago. So it's good if possible to actually go to the church on a Sunday morning and see what happens. You might see or hear things that your contact didn't think to mention, but they are important in sound in the whole picture of the sound system design. Jewish synagogues fall into two broad categories. Orthodox synagogues have the rabbinic prohibition against electronic amplification on the Sabbath and high holy days. The speech and vocal singing will be delivered acoustically, therefore not a concern for sound system design. And if you do, it's going to be a live reverberant room that's, if they want sound for other days, typically they won't install sound at all. Reformed synagogues, speech, instrumental vocal music, building styles and program requirements are very similar to evangelical Christian churches. So a lot of would cross apply from what you'll see in a Christian church. Mosques. These are typically large, open, square, rectangular spaces. They're reverberant, all hard surfaces. They're typically speech only. Interesting difference if you're working in a mosque. The audience plane is at 2.5 feet high. They're sitting on the floor. Most other places, your program will automatically put the audience plane in at 4 foot, which is the seated height of your ear. For a mosque, you'll want to lower that to 2.5 feet. Almost always have a separate women's section. Sometimes it's just curtained off in the back of the main floor. Sometimes it's a balcony. Sometimes it might even be a separate room, but you need to find out what they're doing in that regard as well. And as the sound columns, again, for intelligibility in a reverberant space, and this is FR columns 2-3 units tall or even taller for large rooms. The smaller 200 series columns for small rooms or for fills. Here we have, I think this is the Grand Mosque in Kuwait. We've got an antithesis line up front and then another small fill in the back. They actually, I believe they might sometimes curtain this off as a women's section. Sometimes the women might be in a different space. But I have a picture here of that. We'll get into some pictures now. Just look at this a minute and absorb the scale of this, what you're actually looking at here. Over here is a 3-unit antithesis FR column. This is 11 foot tall, flown out here, and that is 11 foot. This thing is from floor to the top of the wall is, I think, between 55 and 60 feet. So this is enormous. The picture is taken from under the center of the dome. So we're only looking halfway across the room. This is several football fields. It's 10,000 people. You can imagine the reverberation in there. So intelligibility is we require a line array to get good intelligibility in that. This is a Reformed synagogue. If you didn't look at some of the pictures and whatnot here, you could think this is a Presbyterian church. You could think it's a Methodist church. In any town in the Midwest. It's the synagogues are very similar to Christian churches. Here we've got the line arrays on the front. And I point out something here when you get into this what I call a barrel ceiling, where it's got a curve, same radius the whole way front to back. In the center of this room, you're going to have reflections. Any sound down low goes up, spreads out, hits this curved surface, and comes back down again, concentrate to one spot in the center. Now, they have carpet on the floor, which helps a little, but anything in the center, and you can easily demonstrate this if you're in the room, just clap, stand right in the center and clap, and you'll hear it come back off that reflected back off the ceiling. You get in a room like this, you don't want to put anything audio in the center line of the room. Don't put the console, don't put the microphone, don't put the speaker, because of that focusing. And if the sound source is over here, it's going to bounce back and come back, a double hop back. You really want to keep the sound low, keep line arrays, keep the sound away from that curved surface. In this case, that's we've got a bad reflecting surface, and we're keeping the sound away from it with a line rather than fixing the surface. It's there, it reflects sound and keeps the room reverberant for music and whatnot, singing, but we keep the speech away from that curved surface. Glen Rose Baptist Church. This is a church that looks a lot like a school auditorium to me. We've got Entasis Ivy 6 columns on the right. We've got a little fill speaker, I think, to fill in the front center. It's a little dark area that they need a little extra help. This would be a more of a high energy contemporary service with the Entasis with the Ivy 6 line array system. West Jacksonville Baptist. This is a design I did. This is a little more traditional Baptist. It's not a contemporary music situation. They've got the choir loft, they've got the baptistry in the back. Nice big projection screens, and they darkened that area, made a nice little area up here to hide, and then just had an Ivy 6 3-unit arrays. And this is a full stereo system. So this array covers the entire width of the room. I think it might be a little bit dark in this front corner, but essentially it's full coverage. We've got I-series compacts, I believe, here filling in the balcony. St. Nicholas Church, I think a Catholic church in Wilkes-Barre, PA. Entasis columns hidden. If you didn't look at this, but you didn't know where to find them. Right here is an Entasis column posted on the wall on the post. And up here is a double Entasis column, and that's what you see in this. So you can see how well they can hide into the architectural features. We like that about them. People really like them. Just match the color up, and they really disappear. Here's another St. Mary's of the Assumption. Again, Entasis columns tucked in among the beams. Here we've added a BLF 208 subwoofer. The dual 8-inch just warms up the Entasis columns are only good down to about 200 hertz, which if it's speech only, that's fine. If you want to play any program, any music, it helps to have a little bit of low frequency support. So that's what we had this little sub in here. Shepherd of the Hills, San Antonio, Texas. Again, this is a cruciform shaped church. Again, antithesis columns hiding in the posts of the building. We've got this is a 206, antithesis 206, that points out to the side here to fill in the transepts on each side. Don't forget the stage monitors. We supposedly no longer make portable speakers. However, these stage monitors were just too cute to discontinue. They fit so nicely into the church, the lines and the visual look of them. Available in white and black, 8-inch and 10-inch coax. They do have a wall mount bracket that attaches the point here, so we can, you could put them on a wall as, choir loft fill or something of that nature. So that comes to the end of my presentation.
Great. Any additional questions can always email Dale. I want to thank everyone for joining us today, and be sure to keep a lookout for future Biamp webinars. Thanks, Dale. Thanks, everyone.